Hi everyone. This is section 14.4, but it's kind of almost more like 14.3 part 2. We're going to do the exact same thing we did in 14.3. We're going to prove triangles are congruent using our shortcuts, and we're going to learn two new letter theorems. 14.3 was SSS for side, 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 and SAS for side, angle, side. What we have here is ASA and AAS. So let's go through each one at a time. You probably know what the letters stand for right now. We said in 14.3, each S is a side, each A is an angle, and it has to kind of go in order around the triangle. So when I say ASA, it's my shorthand abbreviation for the angle side angle congruence theorem. And it says if you have that exact pattern, angle, then side, then angle, or you could think of it as two angles and the side that's in between them, then they're going to be, if you have the same pattern congruent in two different triangles, then the triangles are congruent. And I'll give you an example of each one, like I did in 14.3. So right here, we have triangle ABC congruent to triangle DEF by ASA. What you have is, in one triangle, you have an angle congruent to an angle, then a side congruent to a side, then an angle congruent to an angle. So again, if you kind of go in order, it's ASA. A, then S, then A. Angle, side, angle. And you don't need to know anything else. I don't need to know anything about angle A or angle D. I don't need to know side AC or side AB or side DE or side DF. We're cutting our work in half. Out of the 6 parts of a triangle, if you have the right 3, that's enough to say the triangles are congruent. Our second theorem for today is AAS, which of course stands for angle, angle, side. And it says if you have two angles of a triangle congruent to two angles of another triangle, and one of the sides that's not in between them, then that works too. That's enough to show that the triangles are congruent. So actually, if you combine our two theorems from today, it's kind of like two angles and a side in any order works, pretty much. But you do want to make sure you have the letters going. You want to make sure you have A, then S, then A, or AAS, just to give the reason for the theorem. So here's an example of AAS. We have angle, one A, angle, another A, and then down here we have side. So going in order, I would probably go this way, A, then S, and then the same pattern, A, then S, angle, angle, side. So as long as you have one of those 4 patterns we've talked about, SSS, all the sides, SAS, or either of the 2 we just learned, that's enough to show triangles are congruent. So what I want to do for today, for our example, we're going to do a proof again, and it's almost the exact same proof we did yesterday. What I did is I took one of the pieces of given information out. So yesterday I gave you this exact same proof, except I also said in the given information that U is the midpoint of line segment YV, and we used that to get one of the S's. Now I'm taking that out, so we can't use that anymore, but I want to see if we can still do the proof without that. So let's set up for our proof. Let's set up for a 2-column proof, statements and reasons. And then our first statement, as always, will just be copy the given information. So we have YZ is congruent to VX, and we have YZ is also parallel to VX. Same as yesterday, put given for our reason, but I took out the part about midpoint, so we're missing one of our S's. But let's still mark up our picture. So I said YZ congruent to VX over here. And then I said also parallel. YZ, we'll put the parallel marker, parallel to VX. So everything's exactly the same as yesterday, except we only have one of our S's. Yesterday, just from the given information, we used the midpoint to find a second S. Today we don't have that, so we're going to have to use more angles. Now the thing I think I would do for my next step, let's actually use the same step we did yesterday. So remember yesterday we said this angle here, angle Y, is actually congruent to angle V by alternate interior angles. Let's say that one again, because that'll give us one of the A's again. So based on the same work we did yesterday, I'm going to say that angle Y is congruent to angle V because they are alternate interior angles. Or I'm going to say by the alternate interior angle theorem. Use some abbreviations to squeeze it in there. Okay, so we have our given. That was one of the S's. We have alternate interior angles, same as yesterday. That's one of our A's. What we don't have is that extra S. So we don't have an SAS. So what I need to do is I need to see if I can get another one of the angles and use one of our new theorems from today. And it turns out for this one, we could actually get either angle. We could, depending on how you think about this, there's two ways to finish this proof. And I'm going to go through both of them just so you can see them. One thing I could do is I could say angle Z is congruent to angle X. Now, if I do that, the reason it's going to be alternate interior angle theorem again, you're just using the other line as the transversal. So instead of using YV as the transversal, if I extend the line this way and use that as the transversal, then it gives me alternate interior angles again. And you could do that, or I want to show you both possibilities. This way it might even be easier. Let's get rid of those. A second way to do this would be to say this angle right here is congruent to this angle right here because they're vertical angles. And I'm going to do that for my proof. I'm going to say, now I can't just call it angle U anymore. In step 2, I can call them angle Y and angle V because there's only one angle I could be talking about. But angle U could be either of those angles. And when you have more than one possibility, use 3 letters. So I'm going to call the first one angle YUZ. From Y to U to Z. And I'm going to say that's congruent to angle, and I'm going to use 3 letters again. I'm going to say X, U, V. That would be from X to U to V. Now the reason for that one is the vertical angle theorem. Vertical angle theorem. Now, because I used vertical angles, what I actually have is an AAS. In order, going around, if I start at the U, it's A, then S. Angle, angle, side, and then on the other triangle, A, then S. So I'm ready to do my proof. Triangle ZYU is congruent to triangle XVU, and my reason is going to be AAS. Now, if you had done the proof the way I showed you the first time, if you had said, instead of doing the green angles in the middle, if you had done angle Z congruent to angle X by alternate interior angle theorem, then it would have been ASA instead of AAS, and that would be fine. It would be 100% right. So a good thing for you guys to remember on these proofs, there isn't always only one way to do them. Your goal is to find enough pieces to do one of those 4 theorems, SSS, SAS, ASA, or AAS. If you can find the right pieces, you got it. And if there's more than one way to do it, any of them work. So let's do a quick summary here. In order to prove 2 triangles are congruent, you need to show 3 things. Now here are the ones that work. These are the ones I just talked about. SSS works, all 3 sides. SAS works, 2 sides and the angle in between. ASA works, 2 angles and the side in between. And AAS works. And actually those last 2, group them together and it's basically like any 2 angles and a side. Now there's 2 things that don't work, and I'm going to give you a counter example of each one. I want to show you why they don't work. The first one that doesn't work is AAA. Even if you can prove that all 3 angles of one triangle are congruent to all 3 angles of another, that's not enough to say that the triangles are congruent. They could be what's called similar, and similar shapes are exactly the same shape but different sizes. So here's my counter example for AAA. Let's say I draw a triangle right here, and let's say I draw a smaller version of the exact same triangle under it. And I said, okay, well, this angle right here is congruent to this angle, that's 1A. And this angle is congruent to this one, that's 2. And this angle, it's going to be hard for me to squeeze 3 in, but you get the idea. So what we have is AAA. 3 angles of one triangle congruent to 3 angles of another, but they are not congruent. So AAA does not work. That's a counterexample. And remember, when you do a counterexample, if you can show even one example of a theorem not working, then you can't use that theorem. It doesn't count. So AAA does not work. And then the other one that doesn't work is SSA. 2 sides and the angle that's not in between them. And I'll show you an example of that too. Here's how I'm going to do. I'm going to draw 2 horizontal lines here. And I'm going to draw a matching angle. So let's say that angle right there is congruent. And I'm going to say this side right here is congruent. So what I've done is I've drawn 1A and 1S. Now I want to finish the triangle using a congruent side. Now let's say for one of them, I draw the triangle going like this. And for the other one, I draw that exact same side length, but kind of going backwards like this. So these 2 sides are congruent. Now imagine those 2 triangles without the extra line drawn off to the left there. What you have is S, S, A, and then you have the exact same S, S, A. Now see, those triangles aren't congruent. That shows you, that's my counterexample. That shows you why SSA is not enough to prove 2 triangles are congruent. There could be a case where you have 2 triangles where 2 sides are the same, the angle outside of them is the same, but the 2 triangles are not congruent. And that's why SSA doesn't work. Any of the other ones do work. If you have SAS, I can't draw a counterexample. It works every time. If you have ASA, same thing. I can't make up a counterexample for ASA because it works every time. So if you're trying to prove 2 triangles are congruent, you always need 3 things, and you're trying to fit any one of these patterns. Get all 3 sides, get 2 sides in the angle between, get 2 angles in the side in between, get 2 angles in the side next to them. Any of that works, it's fine. But not the other 2. If you're trying to do a proof and your reason is AAA, you're not done yet. You need to find one more side and then use like an ASA or something. Same thing with SSA. If you're trying to prove 2 triangles are congruent and you have the SS and A, find one more thing. Find the 3rd side and do SSS, or find the angle in between those sides and do SAS. You just don't have the right pieces with those 2.